And good morning. So I'm still in the process of doing refactoring on the Farkos source base to clean it up a bit. Um, and part of that is reviewing the code I've produced so far and working out which bits of code were, um, using the wrong algorithms because I thought they were pleasant or cool or they pulled to me. Where the correct algorithms are cleaner and easier to use. And the first one, I had a clever idea for matching the orbit when I'm in one orbit, I need to get into another orbit to say go rescue someone. And I thought, hey, I'll just treat this as a landing problem. Ignoring my lateral velocity across their orbital plane, I'll just land on their orbital plane. And that worked really well in low Kerbin orbit. And it had a couple of drawbacks. First off, I was never actually calculating the location of the ascending node or the time of I wasn't calculating the time at which I was going to do the transit. So my ability to time warp was very limited. And in fact, the code explicitly had some things in it that tried to raise the warp, but it never went far enough for distant orbits. And in fact, because we were landing on a plane and our approach speeds our normal speeds got so low for far orbits, it had a hard time actually doing a burn. So LKO, say out to 120 kilometer altitude, we were just fine, but you get out to 5, 6, 7 million kilometers altitude, and I would blow past the point where I wanted to do the burn. It wasn't checking often enough to capture, oh, I need to be burning. And if it went past it, it would say, I'm going to give up for another 180 degrees around the orbit. And my sensitivity was very small. I mean, I was very proud of the fact that I could beam this within 0.1 degrees in LKO. So, yeah, things didn't work so well at farther orbits. And I found myself saying, well, okay, my launch will put me in almost the right plane, and then I could do my Lambert stuff to get out there, and then I'll just, RCS over. And that worked. But it was unsatisfying. I mean, as satisfying as landing on the orbital plane was at low orbit, it was unsatisfying at high orbit. So I coughed out the code we have here in front of us. I am sorry that I have no great pictures of this. The math is pretty straightforward. Again, no pictures. I haven't written up the math in LaTeX, so there's no fancy equations. There's just this. So if I'm in the wrong orbital plane, then my normal vector will differ from the normal vector of the orbital plane our target is at. And that's, you get your normal vector is basically the direction of your angular momentum, which is, in the real world, it's V cross R. You use R cross V most of the time in Kerbal Space Program because, we're left-handed axis, and that gets us back at the thing. But in this case, I actually used, V cross R. Okay, so I did do it right. So HS is a vector that is normal to the ship's orbital plane. Okay. O is my orbit. The targ package, if I haven't covered that, I have been extending targ so that it can handle targets that are not targetable. So for instance, we could set a target orbit which has an inclination, it has an apoapsis and a periapsis. It'll come back and actually give us an orbit object. While we're going over the code, I am going to send this. This is my development craft. It's a little overbuilt for any particular mission, but what it does do is it allows me to put somebody in orbit who can then run programs on here, and I've got a list of subroutines that I can trigger over here on the left. So let's get that going. I'm going to use KER, Kerbal Engineer, to select a destination. In this case, I'm going to fly us out to the C01 satellite. So our orbit is going to be fairly far away, and it's going to be mostly equatorial. So C01 is a very low inclination. And once we get out there, we will, our automatic launch of D gets us to that location, and in the correct orbital plane and circularized. So then we can fiddle around. I want to show you the plane change now that I'm switching to, and then we can look at other things. So HS, going back to the code, is the vector that is perpendicular to our orbital plane, and there's two of those, and you pick the one. If you pick one of them, you're going one direction around like this. If you pick the other one, you're going the other direction around. We do the same thing for the target orbit. Now, orbits have a position and a velocity. Okay, anything that is a orbit structure in KOS will have this. So even if it's not a body, even if it's a synthesized orbit, we can still get this stuff. That's important because planned inclination is going to be used for launching satellites and for doing rescues and for getting to other bodies. Now we're aiming at going to MUN. So HS and VS. Well, NV, if we've got these two normal vectors, we've got my orbital vector pointing straight up, and we've got MUN's orbital vector pointing off to the side. I'm going to do this us and MUN. This is a rotation. Well, I've got two vectors rotating from one to the other. If I do a cross product, it's going to give me a vector normal to that. And that vector happens to lie along the line where the two orbital planes intersect. So that's the line of nodes. So that will point to the ascending node or to the descending node. And as it turns out, if your cross product is the angular momentum of the orbital plane cross the angular momentum of the ship, that gives you back a vector which points in the direction of the ascending node. So the ascending node is where we will do a burn roughly in the direction of our angular momentum vector, so upwards through the plane, to correct our direction. And for 180 degrees around, we'll do a burn downward. And I did a whole bunch of scratch work and math to work out, what the burn was going to be. And then I realized we have direction. Now, a direction is more than a vector. Okay, a direction is a rotation. It's a vector with a up. So it's roll, pitch, and yaw at its base. And directions in KSP and KOS, think of them as a quaternion. Okay, think of them as a rotation matrix, not just as a direction, as a vector. So I thought, hey, can I, with two vectors, figure out what the rotation is it gets from one to the other, and I'm going to apply the same rotation to my velocity vector. So if the nodal vector points toward me, so out of the camera towards me, and there's the correction I want to make, that's a rotation. Well, my velocity right now is going this way, and I want to make the velocity go up this way. This is a rotation of a velocity. Wow, okay, so rotate from to says I have two vectors. What is the rotation as a structure direction that gets me from one to the other? Oh, that's easy. Rotate from to. I didn't even know that was there until I was poking around in old videos, and there it was, being talked about by Dunbaratu, who wrote the thing. Cool. Yay. Oh, by the way, thanks, Dunbaratu, for all of your work on this. This has been hella fun for the last many years, and it will be fun for quite a long time in the future. Anyway, so we get this rot, which is the rotation. This is actually the it's not the delta v. It's the angle. It's actually the rotation that we want to apply to our velocity vector. So now we pick up what is our velocity going to be when we get to time 1. Okay, so time 1, oh, I skipped over getting time 1. We need to compute the time that we get to this. Hey, okay, I could have done this in several other ways, but I did it this way. Rewinding. At this point in the code, we have a vector that points from the body in the direction of the nodal vectors, and we're either out along a positive multiple of it or along a negative multiple of it. And find node, which is down below there, is actually going to be a it's sort of a hill climbing. It's that modification of hill climbing I did that starts at a value and works unidirectionally in one direction through the search space. It says what is the best input vector as I scan to the right. I'm looking for maxima. It coughs up the local maxima, and then we get the global maximum. So for now, while I'm looking at this, I'm just going to say scan forward along my orbit until I find that my position is either a positive scalar or a negative scalar times that vector. We'll leave that for later. So now I've got the time of the ascending node or descending node, whichever one comes first. So now we can calculate the rotation. I just talked about at length. We can get our velocity when we're crossing the ascending node. And now we say rotation times v1. If you're actually doing real math quaternions, it's different from this, but same flavor, same intent. We want to take the velocity vector and rotate it by the rotation direction. So that's done by multiplication in KOS. So rotation times v1 gives us v2. v2 is the velocity we want to have at that point. So what's our dv? Well, it's simple. It's the velocity we want minus the velocity we have. So there is the dv, the burn that we need. So it's a vector of change in velocity that we want to apply at t1. Well, that's all we need to create a maneuver node. So we have a bit of support code over a maneuver that will schedule doing a burn of dv at the time t1 for us. So that actually handles taking this dv, which is a vector in basically ship raw coordinates, and correcting it to what's needed by the maneuver system, which is a prograde plus a radial outward plus a normal vector. And the subnote here, radial outward is not directly outward. You've got a prograde vector and you've got a normal vector, which are prograde and normal. And if you are in a eccentric orbit, it picks this vector. So it's the normal, it's the vector that's normal to these two, which is mostly radial out. I did a whole lot of work to try to put myself in a non-orthogonal basis, and then it turned out that I just needed to do that. Anyway, so schedule dv at time. I'm going to go back, if I remember to do it, I'll go back and see if I ever covered that in a video, because it's kind of again, it uses a rotation to rotate the dv vector into that basis, and it's simple. Once I've scheduled maneuver, I can leave the maneuver node behind. So the entire purpose of this function, top to bottom, plan incl, is to place a maneuver node at the next ascending or descending node with the proper burn to change our inclination to match the target orbit. Now, this means that when we go to do the burn, we're not using an error controller to get exactly the right inclination. Instead, we are attempting to match a pre-calculated delta V. And this is one layer of indirection that is a source of small errors. So, for example, if we don't burn exactly right, maybe some of our burn happens after the nominal time. More of our burn happens after it than before it. We end up in a slightly different orbit, but the error is small enough. We're good so far because our maneuver node execution is pretty good. We are biased. We do tend to have more burn happening after the designated time than before. If it looks like I can identify the systemic error there and identify exactly what the bias is, I may bias our start burn time so that half our delta V happens before and half happens after. I don't know. We're close enough at this point. I'm delivering us within 100 meters of the destination, so we're good enough. Anyway, so there's our inclination change. And I see that we have come to an idle in the stuff going on behind us. I am going to bring up a console really quick in another window so I can take a look at what the autopilot is doing. And yes, our development spaceship is happily sitting here on orbit in its ready pose. Not really posing, is it? Normally, when I get to a ready condition, I am rotating to point myself in the normal direction. I guess this guy doesn't do that. Huh. Interesting. Either that or we don't have any control authority. No, we do have control authority. Anyway, not a biggie. So we are circularized. I can look up here at the Kerbal Engineer and I see that we are in a 320 kilometer orbit and it's circularized and somewhere in the same orbit as... No, I didn't launch to the orbit of C01. I launched to a parking orbit along its orbital plane. So we are 0.2 degrees away from being on the same plane. Okay. So first off, let's take a look at how this plane change handles something very small. So it's 0.2 degrees. The old plane change code would be coming in toward the target plane, skimming along it very quickly, but very slowly lowering itself to the orbital plane. The angle is very low there, and it would try to burst the engines just a little bit, just before we crossed to kind of get in sync. And it'd be kind of a guess. It's an error controller thing. I wasn't pre-calculating when we did it. I wasn't pre-calculating how much the burn was, really. I mean, I had a notion of it when I got there. So now, if I do a planned plane change, boom. So this tells me that in order to change planes from my current orbit to match C01, I need to burn here. And I need to burn 6.867 meters per second in the normal direction. That's normal up. And once I've completed it, we will end up with a inclination where the ascending and descending nodes are 90 degrees around from me. This is as good as it gets, guys. And it claims it's 0.0 degrees, so it's going to be not many things. Let's have MechJeb display to me more information. Where did I put MechJeb? Down here, orbit, and target orbit information. So currently, MechJeb says I am at the target orbit has the inclination of 0.09 degrees. Let's go execute this maneuver node. Oh, and I need to turn off the editor display. There we go. And now you can see MechJeb's target orbit there. Um, that may be too small on YouTube, so you'll just have to listen to what I'm telling you. It says target inclination is here on the target orbit display, and it's 0.09. And in my orbit information, my current inclination is 0.123 degrees. So I did not launch exactly to equatorial orbit. But let's execute the node. So the logic there is first we align ourselves with where we think the burn is, and then we warp to the burn. And we give ourselves some time to align again, because if we are in low orbit, the direction of the burn changes as we go around the planet. I don't know why. It just does. It doesn't seem to do it up here at 320 kilometers, which is good. This means that we spend all of our prep time just kind of holding this position. And here's the burn. Now that looks to me like almost the entire burn was done after the point, because it's a very tiny burn and we do it at low thrust. But we're starting it based on a burn time computed as if we were using full thrust. So it wasn't perfect, but you notice that those ascending descending nodes ended up right where they should be with zeros. MechJeb is telling me that the target orbit information, hold on, let me... Oh, this is target orbit has inclination 0.09 still, and my orbit now is 0.084. So I think it's rendezvous info. Yes, there it is. So rendezvous info tells me the relative inclination is 0.02 degrees from us. That is good enough for this boy. Now, if I were to plan another plane change, it actually prints out more information on the debug console. Let's see if I can print this, if I can show it here. Yeah. I don't think that's going to be visible at all. Okay, that's getting there. One more click. If I am seeing on my monitor what's actually going to YouTube, you should be able to read this last bit. So when I planned the plane change, I am printing to this debug console how big the inclination area is I'm trying to fix, how long until the burn, how much the burn is, and the burn vector. And the burn vector will give me a delta V times a direction. This is my debug printer that does this, and it rounds it. But I wanted an unrounded delta V. This says 4.7 times 10 to the minus fifth. So, KSP says this is a 0.0 meter per second burn. It's going to take a tenth of a second. I am going to cancel this because, frankly, I don't think I can do that burn. Now, I've fiddled around with the idea of something I used to do manually, where if I want to do an itty bitty, tiny, teeny burn that's normal, what I do is I package it with a 1 meter per second burn in some other direction, say 1 meter per second radial outward plus a thousandth of a meter per second upward is still 1 meter per second of delta V at a small angle. And this means that I can very finely control the amount of normal delta V at the cost of getting a big radial change. And that means that later I'll need to come back in and fix my orbital parameters, fix my eccentricity that I've messed up, but it means I've gotten into the right plane. And all I have to do is make sure that I hold that correct plane. Not doing that now because this is a small enough error that we can make our rendezvous. But that's what happens when we've got tiny errors. Remember, we only fixed, a couple hundred, we only fixed a tenth or a hundredth of a degree there. What about if I wanted to, say, synchronize with min-miss? Now, normally, if I'm going to min-miss, I am going to launch into min-miss orbital plane. Let's get rid of that. Now, min-miss is, well, it's kind of, twisted. It is 6.1 degrees inclination away from where we are. So this is going to be a bigger burn. This particular platform, you notice I have almost 3,000 meters per second of delta V in my upper stage. I've got 482 meters per second left in essentially what I consider to be, I usually like this stage to be the one that carries me out to my destination orbit and circularizes me there. This platform is overpowered for its payload. I would have to guess at how high an orbit I could circularize in, but I'm guessing it could circularize all the way out past min-miss. Anyway, we've got 482 meters per second left there. So I am going to be profligate, and I am going to do a plane change here at 320 kilometer altitude to match min-miss. Plane change. Boom. And what does it do? It says this is going to cost me 207 meters per second of delta V. And here's my planned point to do the change. And this claims that once I have made this change, I will be again to within 0.0 inclination, and that's rounding to. So this is less than a 20th of a degree off. It claims it'll get to. And I look at my planning output on my KOS monitor. Let's bring that back up. And this says I'm correcting a 6.08 degree inclination change. So you can see that doing inclination changes at lower altitudes is expensive. And in fact, as if I were doing this 80 kilometers, it'd be even more expensive. So if we wanted to go to min-miss from here, what I normally would do is to get into a circularized orbit out. Maybe I would do a transfer to min-miss's orbit, synchronizing with min-miss, but in my plane, which would place me, well, come on. It would place me out along some line, possibly here, but in my original plane, so I'd be way below or way above min-miss, and eventually I would get to min-miss, and I might even use min-miss capture. So there are things you can do to avoid this 200 meters per second. I'll just leave it at that. But given that it's there, this maneuver node should correctly do the plane change. And because it's a maneuver node, we get the normal time warping before the maneuver node. Let's close that. And let's watch it bend the blue line up to meet the dotted amber line. And there it goes. And our apoapsis is kind of moving around a little bit. Now, because our burn is not precisely normal to our own orbit at all instances, the apoapsis and periapsis will move around a little bit. But in order to keep them stable, I would have to do a burn that is curved. So I'd have to burn along the circle so that basically we would spend a little bit more delta V. Okay. And it's easier to simply say we're going to correct our inclination, and then later on we will worry about our eccentricity and our apoapsis and our periapsis and so on. So we have now corrected this. So that's the first topic I wanted to cover, which is the inclination. You notice here that our relative inclination is showing as 0.00 degrees in MechJeb. Our target orbit are both 6 degrees of inclination. Our display here shows 0 ascending node, and we are in Minmus's orbital plane. So the second thing I wanted to go over was the next bit of work to try to get to a remote body. Now, I actually developed this with MUN, but I'm going to see if I can use the code that I developed for MUN to now do a transfer out to Minmus's SOI. Now, there's a challenge here. All too often when you try to transfer out to Minmus, you end up getting an intercept with MUN. So I may cancel this and try again. The change that I made, fairly simple. It's actually in the targeting mechanism. Normally, if I do an intercept, I use Lambert's to basically walk my starting time around and walk my transit time around until I find a combination that gets me from here to there with the lowest delta V. And because I'm using the Lambert solution to say here to there at this delta time, I can evaluate this when my starting orbit is not circular, when my destination orbit is not circular. It just kind of works. Okay. No matter what you're doing, you can always find that Lambert solution from A to B, and you can say, well, what is my delta V that I would need to get into that trajectory that Lambert is charting for me, and what's the delta V I need to get out of it. For rescue operations, you want your target to be, the thing you are having Lambert get you to is either the thing you're rescuing or something like 100 meters away from it. So you don't want to beam it directly. This stuff can be so accurate that I can do a rescue at low carbon orbit, and you come barreling in to do your final correction to circularize in the same orbit as your target, and just as you come close to a stop, bam, you beam your target because you overshot by 20 meters, and those 20 meters included passing through your target. So I did a standoff thing where I actually aimed for something closer to the body than the target. So as I come in, my aim point is offset. So even if I overshoot, I'm not going to hit the target. And that was the target standoff distance, which is still there. Okay. We now have some special case. What if the target is a body? What if the target has a sphere of influence? Well, if I just planned a intercept orbit going to MUN or to Minmus, the Lambert solver would happily say what trajectory gets me to the center of MUN or Minmus at that time, ignoring its own gravity, but what would get me to that point in the orbit. And this means that as you approach MUN from below, you're reaching your apoapsis. It's actually moving faster than you, so it's going to catch up to you. So looking at it from the viewpoint of the target, you're coming screaming in from the front, kind of offset angle. So if I'm MUN, I'm headed towards you, I see the spacecraft coming in like an angle here. It comes screaming into my SOI and comes powering right down, and it's on a rectilinear orbit almost. I mean, it just comes straight in and smashes into the surface. And it's not the cheapest thing. And I thought, wait a minute, all I really want to do is get myself inside the sphere of influence of the destination body and hang out there for long enough that I can, I just kind of dip into. So I'm MUN, I'm going this way, and I want it to kind of dip into the SOI from the camera. So I'm up here, so I'm coming up. Just dips in, and comes back out. And the little time it spends close to Mun is just enough that I can fire my engines to apply a delta V there to get into whatever orbit I want to be in. I've tried this with Mun when I did the development here, and it works really well. So what I've said is that my inside SOI distance, which is the distance from Kerbin to inside SOI is the distance from Mun to the offset point. So we're gonna shoot not for Mun or Minmus, but a point closer to us, inside its orbit by 90% of the radius of the SOI. So it's target radius plus 90% of the target radius minus the SOI radius minus the target radius. So we've got the body, we've got its SOI, so this area here we're going to do 90% at the altitude. And that gets us a orbit that's not going to get changed a little bit. Oh, you'll see what it does. There's a little flip here in that if I'm starting out further out and I'm descending, let's say I'm near Minmus and I'm coming down to Mun, I don't want to go to the inside of the Mun's orbit, I want to come in from the outside. And at that point we'll be overtaking it. But either way, we're just going to shave the SOI just a little bit, dip in and come back out. And I just realized I haven't shown you the code. There's the code. So target standoff is basically tells you where this standoff point is, this spot, this aim spot for long distance planning. So we predict the position of the target at that time, and then I want to save off the direction from the body we're orbiting to the target and how far it is. Now, if it's a body, then we look at its SOI, we decide whether we are coming, this side of it or the other side of it, and again, TD is the direction from the body to the target times either the radius plus or the radius minus our offset distance. And the old math is still here. I reorganized it to look like this, but basically this is TD times TR is the original position of the target minus the standoff distance. So boom. So here's the original aim point, which is always toward the body from the rescue target. Okay, so now that I've disclosed the code, let's turn it off, and I am going to plan an intercept to Minmus. I think this is the first time I've done this. I've been using Mun as my target. So I've got this little Lambert planning here that gets refreshed every 5 seconds until we finished our planning. And there's our planned burn to get to Minmus, and it is 783.7 meters per second. And you'll notice that the apoapsis of this is short of the orbit of Minmus. Remember, the idea is that we are going to go out to just close enough that as Minmus comes by, its SOI will sweep us up. And looking at if we focus on Minmus, this says that as Minmus gets to this point, we're going to enter Minmus's SOI here. We are going to have a periapsis of 1.9 million meters over Minmus, and then we are going to transition back out. So this is at 9 day, 2 hour, 56 minutes. This is at 9 day, 4 hour, 14 minutes. So this is a couple of hours here. So this gives us some time, a couple of hours, to say, well, here I'm going to burn to circularize my orbit around Minmus, or do something else, or I don't know, maybe I'll go into a polar orbit around Minmus so I can collect a bunch of science, or maybe I will arrange to go down to the surface. But we have all those choices we can make when we are just kind of slowly wandering past Minmus. I don't know what our velocity is here, so we'll find out what our cost is to circularize once we get there. So switch back to focusing on our ship. And let's go ahead and do that. Now notice we dipped into Minmus's SOI and we came back out because if you don't do anything while you're in the SOI, you entered from the SOI and you're going to leave the SOI with the same speed relative to the main body. Okay. Now, because of the way this is working here, this is actually we're actually moving in the prograde direction, so we're picking up some energy. So picking up some energy. Somehow, okay, this is new to me. This transit, which is in the prograde direction, we actually lost some orbital energy. Well, that's fine. Don't mind that at all. What that means is that when we come back, our curb and periapsis is about what it was when we went out. So if we didn't do a burn at Minmus, we would return. This is very much like the way the Apollo missions planned it, where once they got on the lunar transfer orbit, their inertia would carry them past the moon and back into a lower orbit so they could actually return to Earth without doing any burns. So it's kind of a safety thing. So let's go ahead and do that burn. Leaving myself plenty of time before the maneuver node, just in case I need to wrangle my vessel into the proper orientation. Now we are going to have a staging event. Now the staging event shows up on our bar here as a little white mark where we're going to stage during this maneuver burn. I noticed that recently. I don't know how long it's been there, but cool. If we were doing this manually, that would educate me to have my finger on the space bar so I could stage. We got an auto stager, so it's not a worry. And there's the staging, and now we are in our final configuration. You may notice that I have docking ports. So I am setting up for longer term the next few things I want to do. Obviously, we are getting contracts coming up now to go explore Mun. But I also want to be able to start docking. And auto docking is hard. We have now the ability, as we saw during rescue missions, to use RCS to get within 5 meters of our target, and that's great. But for docking, it's not just 5 meters from the target. It is my docking port contacting their docking port in the right orientation at a low enough velocity so that they can couple. So if I wanted to fully automate that, it also means automatically selecting the vessel docking port and the target docking port that can match, and then jockeying around so we are standing off along the axis of the target docking port and then moving in. And I'm thinking about whether I want to have special code on the station side, whether I want the thing I'm docking to, the docking target, to lock itself at an orientation. And if that orientation is relative to the orbiting body or relative to the stars, I don't know. Or if I want it to cheat a little bit and have it actively trying to point its docking port at the incoming vessel. when I'm docking manually, I just kind of say, well, control each one from its docking port and point at the other guy, so the SAS and the RCS maintain the orientations. Then all I have to do is, um, get myself to come in at a slow speed. I will be exploring with that, but it's going to be a while. Automatic docking is catchy. There's also the idea that maybe instead of doing the automatic docking, what I'll just have is the idea that we have the automatic scripting get us to within 5 meters, where the parking point is the docking port facing. So you can find the docking port, and you can target the docking port, and you can get its facing vector. So maybe our parking point is 5 meters out there, and then have to manually move ourselves around, use the SAS or something to point our docking port in, and then manually bring us in on RCS. So there may be manual steps, just like there's manual steps during a rescue. I'd like to automatically dock. I mean, that would be really cool to have a hands-off, hey you, launch and dock at the station, and have it automatically launch and get to the station. So all I need to do is say, hey, I want to refuel, or I want to move all this fuel I just brought up into the station. Anyway, so we have done this initial transit, and what I noticed is, and we didn't watch it happen, the burn area is big enough that we no longer have a actual capture to min-miss. So we are going to do a LAM correction. So we're plotting a correction, which should take us back to that same point, and we see that the orbit around min-miss is what we wanted. And it's kind of it's a 10 meter per second correction. So that orbit is far enough that even a tiny, tiny error in the burn results in us not making the orbit. And now we have a correction. So let's go execute the correction. So all of these, they all use the standoff call and target. So they're going to be getting the same standoff point, which is near the edge of the SOI. So this is a 1 second burn. So we are going to start at full throttle and we're going to ramp it down. So most of this burn is going to happen after the nominal time. Let's see how it does. Okay, so now we do have an interaction with min-miss. And it's a stronger interaction from before. One thing that I have done to the planning here at LAM Intercept that I didn't do to correction is if the second burn is inside the SOI, I was canceling it. So we're going to delete that burn. Okay, so if I don't do the second burn, basically the transfer and the correction try to do a local burn to get me out there, and then they also plant the remote burn to put me at the correct velocity. And in this case, it was that second burn that was causing my return orbit to do wonky things. So without the second burn node there, we see that this is actually nice and clean. So now what I want to do, just for funsies, is I want to go out and get into orbit around min-miss. I'm going to see if I can do a polar orbit around min-miss with my 2,433 meters per second delta V. So we are going to add here, add a maneuver. Now I don't want to circularize because that will get me in a orbit here. I don't have a button here to select the orbit, so we're going to do this manually. Boop. Hold on. Maneuver node, edit. Okay, first thing is, whoops. Try that again. So I want to, let's start off by figuring out what our burn is going to have to be to circularize. So this is going to be a retrograde. Too far. So that gets us into an orbit. I want to rotate it, which is going to be a combination of upwards and back. And as long as I am doing this, notice I am spending 200 meters per second to get into this orbit, I can get my periapsis down. What if I want to go to 50? Close enough. And that looks fairly close to vertical to me. We can tune it up a little bit. There we go. So in one burn, right at that point, I'm going to transition to this orbit here, and we'll just use the circularize button once we get down to here. So we'll end up placing our development platform in a polar orbit around Minmus, just as a demonstration, just so we can see that this is possible. Okay, so focus back on our ship. Now, execute node should work. There are weirdnesses about warping before and after SOI changes. So what I'm going to do, I don't trust it. I bet you it's been fixed, but I don't trust it, and I want to have some stuff working here. So let's create an alarm. This is a SOI change, and we're going to warp to just before the SOI change. Whoops. And it blew right past it. Son of a... Okay, so I'm going to circularize here and delete the node. So, yeah, alarm clocks. That set an alarm for the SOI change failed badly. So, yeah, this is one reason I'm doing my own code so I can fix it. So we're now in a circular orbit. I can delete. Whoops. How come I can't delete that node? Cannot delete maneuver node. Control locked. Oh, that's unfortunate. Maybe I can delete it from the other end. There. I was able to do it from the debug console. I'm going to have to reboot to get the code running again. Oh, the requested volume is out of range and not accessible. So, at this point, we're dead in the water because we don't have a powerful enough antenna to talk to Kerbin from here. Yeah. Okay, so I'm going to call it here. So we know that we can do these things. We know not to trust the alarm clock for SOI changes. We know that it only takes a couple hundred delta V to transition to a polar orbit around Minmus. So that's good. And we know that we need some significant radio antennas to continue to do things out here, because when I boot, I have to have a connection. So we can see there that I've turned on the whole COM network. We can see that C01 has its connections. I don't have a connection to it. So maybe our next short-term thing is to put up a set of relay satellites with larger antennas. Well, no. Before we do that, let's do the MUN mission. Now, just to verify that this all works for MUN, let's do another launch. This time we are going out to MUN orbit. Same thing. I think my antennas are good for MUN. Hey, let's check and make sure I've got antennas. Oh, my development ship doesn't have an antenna. No wonder. So we were depending on the itty bitty little teeny built-in antenna. Let's go add an antenna to it. Revert flight to vehicle assembly. Communication. So we have several antennae available to us. This unit is never intended to return. So what I'm going to do is I'm going to put a pair of high gain antennas on us. Yeah, I'm going to put them here, and I'm going to rotate it so it buries it almost completely inside the guy. So when these deploy, they will swing out through the RCS and all that, but we don't worry about that, right? Rotate. The other thing is I want the antennas to deploy when I turn on the lights. So currently when I turn on the lights, all the lights go on, but I also want to extend the antenna. Now, the other thing I could do here, which I've been thinking about a lot, is I can add some science to this. So in theory, I could send a D platform up somewhere, do some science with it, and then bring the Kerbal home. Well, for that... Well, that makes this into a science return mission. And that's not a bad idea. I'm free-for-alling this. This is not anything I had planned to record. So, if I want to do this, first of all, this guy needs to be able to return, which means no more of that. Maybe I'll put that one later. He needs a science container. Actually, where did that go? There's a utility. Where did my docking ports go? Dum-dum-dum. I can't find my docking ports. Let's grab one of those. So we'll still have a docking port up front. Yeah, that looks kind of weird. For science, decoupler, too big. If I move the decoupler up like that, it doesn't have that wonky ring. Now, I want to move the high gain antennas off of the final return stage because I don't want them there when I am coming down. We'll do that in a second. Science Junior. The antennas. Let's grab fresh antennas for this. Like that. We need a mystery goo. Just one. We need a thermometer and a barometer. And then we're going to move all of this inside. There we go. Now I could move these antennas inside as well. I think I will. But that does mean I need to verify that the action is there. So light, extend antenna. There we go. So there's our science package. As long as we're flying a scientist, we'll be able to move all the science into the container and land with it. There's that. Question, are we good on our center of mass for RCS thrusting? Okay, that looks good. We could move our RCS jets up. Not a bad idea. Let's put them here. So the farther the jets are from the center of mass, the more control authority we have over our rotation, which means the less RCS fuel we use to maintain attitude. Okay. Ah! VAB is always just a little bit wonky for me, and in KSP2 it's just as fiddly for me. I don't seem to have a good handle on snapping parts into each other rapidly and easily without getting them on the wrong point. So we just added a whole bunch of science. I didn't write down what the delta V was before. We still have probably a pretty decent delta V. Let's say this is D04. I'm going to go back and look at D03 again. So open, experimental. So this is 3442 and D03 was 40. Okay, so we lost about 1,000 delta V doing that. So I don't think I can. I don't think I can build that science craft yet. I think I need to have bigger engines because that increases the payload quite a bit. So we'll continue to use D03. Oh well, it was an idea. So back to the problem at hand, getting to Mun. And all we want to do right now is verify that we can get ourselves in a polar orbit around Mun. And let's see, easy way to do that is we pick up the body, rendezvous, sorry. We're going to rendezvous to a celestial body, the Mun. And I'm going to kill off a bunch of this. So we're starting out with 7,300 meters per second vacuum delta V. So 7,300. Remember that number. We're a little wobbly. I could probably put some struts on this guy. There, we're not wobbling as much now. But you can see right here, that particular joint, yeah. So I've been reviewing also our ascent profiles, and the wisdom that I'm seeing on the net is as you launch, try to maintain your time to apoapsis at between 45 seconds and a minute. So as your apoapsis gets higher, if you reduce your throttle, what that means is that more of your thrust will help bring your periapsis up as you go up. Now, this particular burn is just a programmed basically I compute the pitch I want and I leave my throttles at full and I just go for it. It's not bad, but right now our time to apoapsis is now 3 minutes. So since we are launching to the plane of Mun, and we got Mun targeted, we will have selected a orbital altitude. I think this puts us in a 320 kilometer orbit. Yeah. So that's another thing I'm going to want to review is if we are launching to something far away, I probably want to use a lower orbit. It could very well be that D just always goes to a 320 kilometer orbit. When we start writing the code for the Mun transfer, we'll figure it out. Okay, coast. So if you're throttling back during the ascent to keep your apoapsis nearby, what that means is that we'd not be able to warp during the ascent. So that rapid coast up that you saw there under time warp, we would have been burning our engines slowly all during that time. That also means that when we got to our near apoapsis and we started to circularize, we'd be very much closer to circular. Okay, so there's step one, which is circularization. So our Rendezvous info says relative inclination is 1/10 of a degree. I am going to go ahead to do an adjustment to my plane. This is 3.3 meters per second, so we'll execute it. Now you notice as we are rotating, it changes it because I think it's a difference between the center of mass of the vessel and the control point of the vessel. And as you rotate, your control point moves relative to your center of mass. But once we've locked in, it's pretty stable. Now this is 5.4 meters per second burn that we're doing, now that we are aligned with the node. So burn time is 0.3 of a second, which means we are going to start off at 30% throttle and roll down. So almost all of this burn will happen after the designated burn time. And yeah. So we ended 10 seconds after the burn was supposed to end, but we still ended up with a relative inclination of 0 degrees, which is good. So now we plan our transfer to MUN, which takes 15 or 20 seconds. This is not doing a full pork chop plot internally, but it is doing a bit of scanning, looking for the best. And here we go. So you notice our outbound orbit. This ellipse would be short by this distance here. So that vector is this vector. So we are just going to tip into the MUN's orbit. Execute node. Let's see if this time we can execute the node without losing our intercept with MUN. (722 meters per second). It's going to be a 50-second burn. Let's turn off some of the cruft on the screen here. So we started with just under 7,300 vacuum delta V. And my question is, how much do we have left after we circularize at this periapsis point? So the plan was to put us at 1.6 million meters from MUN. And let's see how close we can get. Remember, very, very small errors during this burn will put us a long ways away from where we want to be at the other end. Throttling down, creeping up on our solution. Almost there. Okay. It's a different orbit, and the MUN periapsis is much farther. So I think we have a systemic thing where we are falling short on where we are getting to. So again, let's plan a correction burn. So we would do a 6.6 meter per second burn, which would bring us into here. And again, let's get rid of that. So this would lower our periapsis around MUN somewhat. You know what? I'm okay with the uncorrected orbit. Let's go ahead and just warp to near. I'm doing this manually. We know what happens with the alarm clock. We just basically skittered on past, and it was actually heading for the second SOI transition, which is not what we wanted. Okay, so here we are. This is 36 minutes out. So if I go to times 10 time, yeah, approaching at 100x, I can look at this and eyeball it. I want to stop us when we're very close. Okay, so here's our transit. Here's our hyperbolic orbit past Mun, and I'm going to do a circularization when I get to here. You know, I should be able to just warp to this location. Whoops. Okay, so when I did the SOI transition, it erased my destination here. That's not good. So, does this work? So, 2258. Okay, good enough. Warp to that. As long as you're not changing SOIs, the alarm clock seems to work. Okay, so we are near the periapsis here. If I circularize, I will be in a prograde orbit. I want to get in a polar orbit. So what I really wanted to do is add a maneuver. Do this by hand. Again, we will need to set up a proper planner to design these orbits. And periapsis, we wanted 50 kilometers. So it's going to cost us about 300 meters per second to get down to there. And then it's going to cost us circularization. So, yeah. We should be pointed kind of up and to the left here. There we go. So our actual first contract to come out to Mun in a ship that we're not going to revert is just a flyby. So we won't be doing all of this stuff. So I should have looked at what the delta V was when we entered. I will look in the recording to find that out. Well, we know it's 300-ish, 24, 27, 27 from 73. Can't math in my head right now. Grabbing a calculator. So we currently have 2,400 meters per second left. We had 7,300 coming in. So we've used about 4,900 minus the 300-ish we just did. So 4,600 vacuum delta V gets us a MUN flyby. Another 300 gets us this low periapsis. And I am going to warp around to our MUN periapsis and circularize Yeah, circularize is very picky about its attitude. It does not want to burn anywhere but directly retrograde. Well, directly along the vector that fixes our orbit. I'll put it that way. Okay, so we're going to call that 2200 meters per second left. So it costs us about 5100 meters per second to get into a polar orbit around MUN using the rather inefficient planning that I just did. So what I'm thinking is we over provision a bit, set us up with, say, 6,000 plus meters per second for a MUN flyby. Guessing. Now, looking at the delta V map, this says 3,400 to get to Kerbin LKO, and 860 to get to transit to MUN, 280 to get into orbit. So this says 4,500 to get into MUN orbit. So yeah, I wasted quite a lot of delta V here. If I had been more clever about picking my transfers, I could have swooped in and ended up with my hyperbolic orbit around MUN passing through my desired periapsis. But I didn't do that because I'm trying to set this up to automate this cleanly. I didn't want to do a whole lot of extra stuff, and I have tried hill climbing my transfer correction to get the desired orbit, and it just doesn't want to do the inclination. It just, you know, it's just really being a butthead. So for now, what I'll do is I will accept that I have to overbuild slightly, and I'll do that because I like overbuilding. Anyway, I'm going to revert back to my launch bay, and this mission will never have happened. And that's the stream, which went roughly 3 times as long as I expected. So, see you in the next one.